So, what if I told you that there's this hidden language that governs pretty much everything, from a pirate's treasure map all the way to your phone's GPS? Well, today, we're going to decode that language. We're diving into scalars and vectors, these invisible instructions that are secretly shaping our world all the time.
Okay, let's start with a really simple question. Imagine you find an old pirate map, and it says the treasure is buried 10 miles from the big palm tree. Is that actually enough information for you to grab a shovel and start digging? I mean, think about it. You could walk 10 miles in any direction, north, south, in a circle, and you'd probably just end up completely lost.
And that right there is the whole problem, isn't it? Go 10 miles is a totally incomplete instruction. But go 10 miles northeast, now we're talking. Now we can actually find something. That one tiny extra detail, the direction, it changes absolutely everything. And that's the core idea we're digging into today. So that first piece of information, the 10 miles, is what scientists call a scalar. A scalar is really just a number. It has magnitude, which is just a fancy word for size. It simply tells you how much of something there is. Think about things like your height, your age, or the temperature outside. They're just numbers, pure and simple. But the moment you add a direction, you get its much more powerful counterpart, a vector. A vector has both magnitude and direction. It tells you how much and, crucially, which way. So our perfect treasure instruction, 10 miles northeast, that is a classic vector. And you would be amazed how many things we talk about every day fall into one of these two camps. Over on the scalar side, you've got things like mass, time, and energy. But on the vector side, you've got force, right? You can't just push something. You have to push it in a direction. And then there's velocity. That's the huge difference between your car's speed being 60 miles per hour and its velocity being 60 miles per hour heading north.
All right, let's make this even more real with an example that I think we can all picture. The big difference between the long winding path you take on a hike versus that perfect shortcut that gets you straight to the amazing view.
So, just imagine this with me. You're out camping and you're starting at your tent. Your goal is to get to that beautiful, cool lake you can see off in the distance. The only problem? There's no straight path to get there. So the trail, it takes you on a bit of a detour. First, it forces you to walk 3 miles due east. Then the path makes a sharp turn and you have to walk another 4 miles straight north. Okay, so if someone comes up and asks you how far you walked, you'd be talking about the total distance. And distance is a classic scalar. It only cares about the total amount of ground you covered. It doesn't care at all about the direction you went. To find that total distance, you just add up the numbers. 3 miles plus 4 miles gives you a grand total of 7 miles. Super simple scalar math. But what if a bird just flew in a straight line from your tent directly to the lake? As the crow flies. That direct path from your starting point to your finishing point has a special name. It's called displacement. And displacement is a vector. It has a length for sure, but it also has a very specific direction. So this brings us to the big challenge. You obviously can't just add 3 and 4 to get the displacement because the directions, east and north, are totally different. So how in the world do we combine two vectors like this? Well, the good news is there's a surprisingly simple and really visual way to figure this out. So let's check out the rules for combining vectors. It's called the head-to-tail method, and it works exactly like it sounds. First, you draw your first vector to scale. Let's say a 3-inch arrow pointing east. Then, starting from the head, or the pointy end of that first arrow, you draw the second one, a 4-inch arrow pointing straight up for north. See? You've placed them head to tail. And the answer to our whole problem, the final displacement vector, is the arrow you can now draw from the very beginning, the tail of that first arrow, all the way to the very end, the head of the second one. This new vector we just made is called the resultant. Now, drawing is great for getting the idea, but what if you want a super precise number without needing a ruler and a protractor? Well, since our paths were east and north, they form a perfect right angle. Is there a kind of math cheat code for that? Oh, there totally is, and it's probably an old friend from math class, the Pythagorean theorem. It tells us that for any right-angled triangle, a squared plus b squared always equals c squared. This is the perfect mathematical shortcut for finding the exact length of our displacement. Let's just plug in our numbers. A is our 3-mile walk east, so 3 squared is 9. B is our 4-mile walk north, so 4 squared is 16. Add them together, 9 plus 16 equals 25. and the square root of 25 is 5. So the magnitude, the actual length of our displacement vector, is exactly 5 miles. Way shorter than the 7 miles we actually had to walk.
Okay, so this is way more than just a clever trick for a hiking trip. This whole way of thinking, using vectors, is absolutely fundamental to how our modern world operates. Let's take a quick look at why this all matters so much.
I mean, vectors are literally everywhere. Your phone's GPS is constantly calculating displacement vectors to figure out the fastest route. A pilot has to calculate their own velocity vector and add it to the wind's velocity vector just to stay on course. Weather forecasters use vectors to predict a hurricane's path. Engineers use them to calculate all the different forces acting on a bridge to make sure it's safe to drive on.
So here's the bottom line. Scalars tell you what, but vectors tell you what and where. They provide the context, the all-important direction that lets us navigate and build and understand our world. Without them, we would literally be lost. So I'll just leave you with this question to think about. From the moment you woke up to right now, how many of these invisible vectors have guided your day? From the weather forecast you checked this morning to the route you took to get where you are. You might be surprised just how much you really rely on them.